Hi, this is Nick Pizzi, and today we're sharing a topic that's a little bit more advanced. This is filter concepts for operators. I'll share this screen with you here and so that we can get started with this video. This is part of our operational series of some more advanced topics, as I mentioned. And today's topic is design and operation of granular media filters. This is filter theory for plant operators, not for scientists, not for engineers, but strictly for plant operators. These are concepts that will help you do a better job running your filters in your water treatment plants, help you understand things a little bit better. I take this topic from, or this quote on this topic from the Water Quality and Treatment Handbook from American Water Works Association. And in there you'll find this quote: "It can be argued that particle filtration processes are possibly the most critical component in potable water treatment facilities because of their ability to remove microorganisms, especially pathogens that cause acute health concerns." So right away, we see filters as being a major component in the protection of the public and the public health from bacteria and microorganisms that can pass through filters. So it's good for us as operators to think in terms of a little bit of a theory model. Model is just a concept that can be used to explain certain things. Doesn't necessarily mean that this is exactly how things happen, but I think this is, of all the models proposed, this is probably the one that is most operator friendly. So I want to share that with you today. So let's think in terms of filtration being a solid separation process. In other words, we have contaminants that are suspended, not dissolved, but suspended in the water that we're treating. And some of those suspended solids that escape sedimentation process and go over to our filters need to be captured. There's some process goals associated with filtration, and we normally call those regulations, but I would urge you to think in terms of setting your own process goals for filters that are a little bit more stringent than what the regulations call for. For example, the stringent goals that you find in the Partnership for Safe Water, an AWWA and AMWA initiative, something that I would highly recommend to you, especially if you're a surface water plant. We know that filtration has to remove the parasites that otherwise cannot be disinfected, and that's the whole point for filtration. Some of the parasites that are found in water supplies that are harmful to people are going to escape the disinfection process. They cannot be disinfected. Without the filter, those parasites would get onto the public and make everybody sick. And indeed, that used to be what happened in this country hundreds of years ago. So the filters then are our last barrier to help us protect against that from happening. So filter operations are going to have a direct effect on the overall health of the community in which you serve. And I think when we tell operators that, when operators grasp the concept of the effect they have on public health in their community, they tend to take filtration a little bit more seriously and tend to do a better job with it. So I would urge you to think in terms of being part of the overall health of your community. Today's topic, by the way, does not include membrane filtration. This is strictly granular media theory. Let's start by looking at filters and particle sizes. Let's look at the particles of the material, the contaminants that we want to take out of the water as compared to the granular media itself that makes up our filters. If you look in the lower right corner there, you'll see an arrow coming up. It points at a graph that starts at 1 millimeter on the right-hand side, goes to the left 1 notch, which is a power of 10 smaller. So it goes from 1 millimeter to 100 microns to 10 microns to 1 micron. So it's a gap of 10 going each time. And you see that granular filter media is generally around that size. For example, we have anthracite in filters that tends to be around 1 millimeter size. The sand that supports that tends to be about a 0.5 millimeter, so it would be halfway between the 1 millimeter and the 100 micrometers. Look at some of the particles that are suspended in water. Suspended particles, microparticles, algae, bacteria. Look how much smaller they are than the granular media filters, granular media in our filters. Bacteria looks like it's 10, 100, 1,000 times smaller than the media itself. Certainly nanoparticles like viruses, hundreds of thousands of times smaller. So how do filters work anyway? If the particles are this small, how are we able to trap them and take them out of the water with media that's that big, comparatively speaking? Another way to look at it would be this: the relative size of particles in settled water. If you take for granted that these 3 white spheres are 1 millimeter in length, and the typical particle that we're trying to take out of water is about this big. clearly something's going on in the filter that's helping us strain these or take these particles out of water. Simple straining is not going to do it. Simple straining would be like being in your kitchen and open up a can of corn. You pour the corn through your sieve, the water goes through, the corn stays behind because the corn is bigger than the sieve sizes. This is just the opposite of what's happening in a water plant. There must be something different happening. We need to understand that as operators so that we can affect that job and do a better job at it. Here's a model that we can use to explain what they call transport and attachment of particles in the water. That white pentagonal particle there is a piece of anthracite, say, and those little red stars, little red droplets of particles in the water. I'm going to use this model. It's very crude but effective model and to explain to you how particle transport and attachment works. So if we accept filtration as transport and attachment of flock particles in the water, we understand that both of them are necessary in order to produce low turbidity. Basically, what they're trying to tell us is that those particles has to be transported from the water to nearby anthracite and sand particles in order for them to then be further attached to the particle itself. So we have to take those out of the supply of water, transport them across that line that you see there I just put in, and get them close enough to the media to attach them. The problem is, when the water approaches the anthracite particle, it takes that path. It has to go around. It can't go through it, obviously, so it has to go around it. So when it does that, it has to speed up. And therefore, the particles that are in the water speed up along with it in order to get around that anthracite particle. The water can't slow down. It can't stop because there's water on top of it pushing down on it. Constant flow. We don't make water in batches in water plants. We make a constant dynamic process. So as that water gets around that anthracite particle, it speeds up, so does that particle. And therefore, we have a much more difficult time transporting that close enough to the anthracite to be attached. Transporting particles across those lines of flow is very difficult, but it's essential. We have to do it. If we look at some of these particles being pulled down, we see that as they approach, sometimes they just blip around like that. Other particles that are on there on the left-hand side, you notice sometimes attach, break loose, and then reattach. Clearly, some of them don't, and they keep penetrating deeper and deeper into the bed. That's called depth filtration, and that's good because what we can do is keep adding more material to our filter, more media, more depth of anthracite and sand, and we increase the possibility, or the probability, I suppose is a good way to put it. We increase the probability that one of these particles is going to get close enough to one of those anthracite or sand particles to be attached. Now that goes on in the process dynamically all the time. They're attaching, unattaching, and reattaching. Hopefully you have enough media in your filter to do that job, and most of them are going to stay out of your clear well. You can see also from this model that if you run a filter too long, some of these particles are just going to hopelessly unattach and get swept into your clear well. So that's a good argument against running your filters for too long. Let's look at this model too. This one helps operators a lot. This again is particle transport and attachment in filters. If you look at the drawing there, that's my poor attempt to make an anthracite particle there, which we're going to call a collector. Its job is to collect that black particle, that circular particle that you see there. And that particle tends to take a path like this, as we've mentioned. As it approaches the water, it tends to speed up and go around. And hopefully we can get it close enough to the anthracite particle to attach it. Now there are forces at work here that both help us and hurt us. And I need to discuss those with you so that you can see what you can help with and what you can't, what you have to overcome in order to attach these particles. The first force that I'm going to put up there in this red line is a vector. I'm going to explain vectors. Vectors have both direction and size. In other words, that force that you see there, which I'm going to call fluid drag, and I got this F sub D there for fluid drag, says that red line can get big or it can get small depending on how you run your filters. I can make that line very big and very harmful. By the way, the red arrows are very harmful to you. So if I make that line bigger by running my filter too fast or loading it too aggressively, then fluid drag is going to become greater because the water is having to move through faster. So that's something that's within my control. As an operator, I can slow that down by putting on more filters if necessary, or at least to keep it in a reasonable amount of parameter, either side of speed. I want to make sure that I'm right into the range of speeds that are necessary for running our filters. Another force at work here is gravity. That force is a green arrow. Green arrows mean they're helping us. And gravity is something we don't have to do anything about. It's there. It brings water straight down. That's how filters work. So it's going to help us. We can't change much in the way of gravity, but just know that it's there working for you. Another arrow, another vector working against you would be the electric double layer that exists between all particles that are in suspension. This electric double layer is what helps keep things in suspension, helps make suspensions of particles. And our job is to get in and get that very stable suspension that exists in Mother Nature and destabilize it. If we can destabilize it, we can strip away or at least make that arrow smaller so that it doesn't work against us. If we don't do something with that water, if we don't destabilize that water, those forces are going to work against us and make it very difficult for these particles to ever settle. In fact, true colloidal particles will suspend themselves in water and stay there for a very long period of time. We're talking days and weeks if you don't do something with that. Of course, that's something that you have to do is coagulate and flocculate your water properly with the proper coagulant. And it pretty much suggests to you that a little bit or too little or too much coagulant is going to hurt you. Your job is to make that arrow smaller so that the last arrow, which helps us, called London van der Waals force, can kick in and help us. Now, that London van der Waals force is a natural occurrence attraction of particles. If they get close enough to each other, they'll grab onto each other through electrical forces, and hopefully that's going to help you. You can get that to work for you if you can get that particle close enough. But to do that, you've got to overcome fluid drag and you've got to overcome the electric double layer. Now, that's not exactly accurate because there are a lot of scientists that will argue with us, but it doesn't matter. The point is, those are the kind of things that go on in filters to some degree. And if you understand them as operators, you can help or hurt yourself by paying attention to these, that's for sure. Okay, some operational filter theory. Try to think of your filter as a particle storage device, not a particle removal device. While you're running a filter for, say, 60 or 80 or 100 hours, however long you run your filters, it's storing particles that it trapped. But you haven't really removed those particles from the water until you take that filter out of service and backwash it. While it's running, you're just storing particles, and there's always a price to pay for storage. The longer you run that filter, the longer you're storing those particles, the greater chance you have of having an upset in that filter and washing all of those particles down into filtration or down into the disinfection area. You have to be very careful with storing these particles. While you're doing that, try to be very careful with your filters. Modern filters are designed as dual media units usually, and this provides deeper bed filtration and longer runs. Excuse me while I drink some of this good Cleveland water here. Deep depth filtration in deep beds provides longer runs because the anthracite, which are larger particles that create larger pore sizes between them, tend to allow particles, suspended particles to filter deeply into the bed before we get to the sand layer. The old model filters that we used to have, the monomedia beds of sand, used to trap a lot of particles on the top layers and get bound off pretty quickly, and we'd have to take them out and backwash them frequently. But modern filters that have dual media designs are made that way in order to get longer runs, and they want you to provide depth penetration. So because of that, you should take care to run your filters according to the design data that they were built for. You shouldn't run them too small or too conservatively. You shouldn't run them too aggressively. If they're designed to be 4 gallon per minute per square foot or 5 gallon per minute per square foot, that's how you should run them because they were designed to allow the penetration down into the depths to filter properly. If you run it too conservatively, those particles will never get down there and you'll just bind off and have short filter runs. If you run them for too long, you're going to start trapping too many particles in that sand and anthracite interface, and you're going to have problems with losing your particles into the clear well. So good filtration then is going to, of course, depend on good pretreatment. If we don't do a good job in flocculation and coagulation, we're going to have poorly treated water. We're not going to filter that water very well. The best filters in the world, the best designed and maintained filters in the world, won't filter poorly treated water, poorly pre-treated water. So that brings me to a subtopic here would be as superintendents of your plant, you should learn to recognize and interpret increases in filter effluent turbidity. And this is a mistake that I see being made by a lot of operators over the years. When they get an increase in filtered water turbidity, let's say combined filter effluent, they have a bank of filters online. They often make the mistake of thinking incorrectly about what's causing the problem. There's probably two things that are going to cause the problem. Either the filter is bad or the pretreatment is bad. Usually not both. Hopefully not both. If all of your filters are putting out bad water, they're suddenly just, not suddenly, but gradually putting out worse and worse and worse water, all filters are doing that, you can pretty much start looking at the pre-treatment process. Perhaps you're not coagulating properly, perhaps there was an interruption in alum feed or something along those lines. If only one filter is bad and the rest of them are good, you can pretty much think that your pre-treatment must be okay. Maybe there's something wrong with that filter. Maybe somebody upset it overnight when they backwash it or something like that. I've often seen operators make the wrong or the incorrect move when they see something like this. They have all of their filters putting out bad turbidity. They automatically think something's wrong with the filter, or their filter, they're washing or filtering at too aggressive rate, so they put on more filters, which is exactly the opposite of what you should do. If you're having trouble with pre-treated water and you're not ripening your filters properly, and the turbidity in the combined filter effluent is going higher, putting on more unripened filters is going to make the matter worse before it makes matters better. The filter rate is called for, not an increase in the number of filters, because those filters are unripened. They're going to pass a lot of turbidity before they can get a chance to ripen. So think about that. Think about in terms of the fact that your water is only as good as your worst filter online. So learn to recognize what filter problems are and how to fix them. Let's talk a little bit about filter design. This is important. There's been a lot of newer technology developed in filtration systems over the last 15 years, 20 years. If it's time for you to renew the filters in your water plant, don't settle for the old technology. I know it's tempting to say, well, these filters have worked for 10 or 15 years for me, 20 years. I've lost a lot of media. I need to replace it. I'm going to put the same thing back in because I know it works. That's fine. That probably won't get you in trouble this year. But in a few years down the road, if turbidity requirements get even more stringent, which I think they're going to do, it's important for you to take advantage of the newer technology that are being developed today and have them engineered and designed into your new filters so that when things do get more stringent, you'll be prepared for it. You won't have older technology sitting around. Putting in the same technology that's now 15 or 20 years old is not going to help you in the future, I don't think. So as operators, we should expect that our design engineers provide us with the right type and correct construction of our filters. If you have an engineering firm that's a little old-fashioned and wants to stick you with the old design, you should fight that. But I'll say this, once the regulator approves your design, once the design engineer does the correct job of constructing the filters or designing the filters and constructing them, after that, any problems that occur in filtered water turbidity is the operator's fault. It's no longer the fault of the design engineer or the regulator. So make sure that you get involved with the engineering process to begin with. That's why I want to teach you a little bit about design, because that's the time to speak up. What takes those guys a month or two to design and half a year to build for you, you're going to be stuck with for the next 20 years. So learn to get your 2 cents in there. Excuse me for my voice today. So we need to be familiar with some of the filtration terms, because when the engineers come to talk to us, we're going to be lost if we don't understand what they're saying. So effective size, or ES, that's the 10% size of the median. I'm going to show you how they come up with those numbers to begin with. So 10% of the media size by weight is the effective size, and the uniformity coefficient, which should be preferably not greater than 1.3 in modern filters, is the 60% size divided into the effective size. So they have to grade out this media. You got to figure out what 10%, 20%, 30% sizes are, and I'll show you how to do that in a little bit. But the uniformity coefficient and the effective size have to meet certain specifications, and your regulator will have requirements for that. They should meet those. You should understand what they're talking about when they mention that. The intermix ratio, this happens in a dual media filter. When you think of a dual media filter with anthracite on top of sand, the anthracite layer sits up here and starts out with the smallest anthracite particles being at top, working their way down to the biggest anthracite particles sitting on the bottom. So those biggest particles would be the D90 size. The D10 size, or the effective size, would be up here, the smaller ones, the bigger ones here. Then when the anthracite ends, the sand starts. So again, the D10 size, the effective size of the sand, is going to be right here, and work your way down through the bed, and the D90 size of the sand is going to be down here. So this interface with the D90 coal size sitting on the top of the D10 sand size is very important. That is an intermix ratio, and that ratio should be about 3. So the size of the D90 coal on top of the D10 sand should be roughly 3 to 3.5. If it's too small or too big, you're going to have problems. This is what happens with a lot of engineering firms that are not specialists in filtration. They tend to pick the wrong media and put it in there, and you have an intermix ratio that's way off. If you don't catch that, you're going to have problems. L over DE ratio, this is just another way of saying, is my bed deep enough? The depth of the bed converted to millimeters and divided by the effective size, that number should be greater than 1,000. And your filter designers usually will design an extra 10%, so maybe about 1,100. In other words, take the depth of your bed, and then if it's a dual media, you got to take both depths, the anthracite and the sand, and convert those to millimeters and divide it by the effective size. That number, which is unitless, should come up to greater than 1,000. If it doesn't, if you've lost media over years, your number is going to creep down to 1,000. At that point, you should think about replenishing the media in the bed because you can't filter too well after that. Bed expansion, that's the term we use when we're backwashing. If my bed is X amount of inches deep, I want to expand it so much so that it cleans properly. And generally, that's going to be roughly 30% or so to start. Something you should figure out for your own plant because every plant is different. Maybe 20% and maybe 40%, somewhere in there. That range usually is what they work out to. Try to figure that out for yourself. The engineer should give you some advice on that. But when you backwash the bed, basically what you're doing is expanding it by lifting some of those particles up, or all those particles up, by the water rushing back upwards against it. If you expand the bed too much, the bed won't clean itself. If you don't expand it enough, it won't clean itself. There's got to be a goal that you need to reach, and that's the bed expansion percentage that you should figure out for yourselves. Solids retention, that's the amount of solids that are retained in each layer of the bed as you go down through, usually every 6-inch depth layer. You want to take that out and you want to measure it, and we'll show in a second video, a more advanced video, how to actually go out and measure solids retention. But basically, when you backwash the bed, you want some solids to be retained in the bed. That's filter ripening. We don't want to wash away all of our ripening, because if we do, we have to re-ripen the bed. And if we don't have filter to waste, that's going to be a problem for us. So solids retention is a very important key topic. We'll talk about that. And the other is unit filter run volume, or gross production, or whatever they want to call it. It's the number of gallons filtered by the number of square feet area of the filter. Usually needs to be at least 5,000 to get approval from your state regulator. Generally, when you run these, if you can get 8,000 or 10,000 unit filter run volumes, you're doing pretty good on your bed. That's good. Some operators like to run 15,000 or 20,000. I think that's a little bit too much, but that's up to them. Here's how they figure out the sizes of the material in the bed. This is the laboratory sieve analysis topic that tells the engineers what size of media that you have. The effective size, uniform coefficient, all of the sizes are determined by this sieve analysis. So each of these pans that you see here is really a sieve inside. There's a screen that's been engineered to be very close in tolerance and put inside those pans. And each pan represents a different sieve size that increases in size. So the top pan has the biggest sieve sizes. The next pan down has a little bit smaller sieve sizes. The next pan down all the way down. So you'd start off with maybe 1.8 millimeter and work your way down all the way, maybe down to 0.3 millimeter. What you would do is take a representative sample of the material that you want to measure. And say you bought a couple of super sacks of anthracite. You pick a sample out of there, you weigh exactly 100 grams of it, and you would put it in the top sieve. You would shake this whole sieve arrangement. And those particles would work their way down. The bigger particles, of course, would stay on top, and the smaller ones would work their way down. Eventually, each pan would sieve out or capture so much of this material by weight. Important, by weight. But basically, what you're trying to do is figure out which percentage does each pan gather out of that original 100 grams. If one pan gathers 10% of the 100 grams, or 10 grams, you've got the 10% size right there. So you filter all the way, you shake all those down. You would use the top pans for anthracite, the bottom pans for sand, I believe, and that will give you the sieve size. And your engineering firm or your lab testing firm will send you a report that looks something like this. This is a grain size distribution test report. Notice those two red arrows there. The one on the lower portion is at the 10% size, and the other one's at the 60% size, because I want to get the uniformity coefficient and the effective size. So what they do is measure out this 100-gram sample, run it through the sieves like we mentioned. They plot it out on this logarithmic graph. You notice in the middle of the graph there's an inverted S-shaped curve. And on that S-shaped curve there are dots. There's 1, 2, 3, 4, 5, 6, 7 dots on there. Locate those 7 dots. Those 7 dots stand for a pan, one of those sieve pans that you saw in the previous picture. Obviously, for this test, they used 7 sieve pans. And they ran those through. They took each pan out, and after they ran the sample through there and carefully weighed that material and put those dots on the graph and drew that line between them. And then they went back and found the 10% line on the left-hand side there, the 10% line, which is the red arrow. And they took that arrow straight across to where it hit the S-shaped graph. And then they went straight down and found that value. And that value would represent the effective size. And they would plot that out there for you and show it to you. There's your D10 size, and it came out to about a 0.5, as you notice. This is for filter sand, not anthracite. They went back and looked for the 60% line and ran that arrow across to where it hit the graph. And they took that straight, hit the S shape on the graph and took that straight down and came up with a 0.654. So now you got the 10% size, you got the 60% size, and you use that to calculate the uniformity coefficient, and they put it right there at 1.31. That's how the sieve report looks like. That's what it looks like. That's how it's generated. So when it comes to you, you'll know what you're talking about. You know what they're talking about, which is important. Let's look at some electromicrographs of silica sand and anthracite. This is about a 0.5 millimeter sand. Notice the good and the bad about the sand. The sand, as we know, is very, very hard and durable. It's not going to break up over the years. It's nicely shaped and fairly rounded when you think about it. It doesn't have a lot of crannies and nooks in there to trap particles, so that's not a real good thing. But the fact that we can crush it up and make it very small and very uniform in size helps us in our filtration process. You're probably not going to lose sand over the years unless it leaks out the bottom of your filter. Here's anthracite, a little different. This is a bigger particle. These are 1 millimeter anthracite particles. Notice how angular they are compared to the sand. The bad news is the anthracite is softer than the sand, but it's more angular. It's more apt to trap particles, and that's what's good thing. So we can afford to make it bigger. That's nice. Notice those nooks and crannies you see in there. Very good for trapping microscopic particles. When you're filtering, that's exactly what does the job for you. They get hidden in those nooks and crannies, they get attracted. So the surface area of that, even though it's a 1 millimeter size anthracite, because it's got so many nooks and crannies in it, the surface area is actually very big. If you could expand it all out, flatten it out, you'd have a very big particle. So there's a lot of surface area for those particles to get trapped into, and that's good. Bad news is, I said, that it's soft, and so some of these little corners that you see here are going to get chipped off over time. That's called making fines, and the fines in your bed easily get washed away. So over time, what started out as maybe a 1 millimeter piece of anthracite now has lost a couple of fines off it. It's now maybe a 0.7 millimeter piece of anthracite and 0.1 millimeter piece of fines being washed away. So that's the thing you got to remember about anthracite. Its shelf life isn't that great. With more washing, it just tends to get smaller. Okay, here's a brief case study, graphical review of a pilot facility that led to a design. Again, this is our Lake County water treatment plant. The man who was always gracious enough to lend us their data so we can use it for operator caption education purposes, and we appreciate that. They had asked Ohio EPA a number of years ago to approve a new configuration for their Aquarius water treatment plant. They had older technology and wanted to replace it. The old filter system theoretically had enough capacity, but they knew that that design at the time was 30-year-old technology. It had been built in 1984 and 85. So 30 years later, they desired to replace it. They didn't want to put the same design back in there, so they decided on a new study to figure out what could be made in new improvements. The existing filters had lost a lot of media. More headspace was needed. These are triple media filters, and I'll get into that in a minute. So then when they piloted this new configuration, they used this kind of an arrangement here. That line that circular thing you see there is their actual settled water line in their water treatment plant. It's a big 36-inch line that feeds the filters. Settled water comes over to the filters from the said basins through that line. What they did was tap into it with that corporation stop and run that water over to a constant head tank that they mounted about the same height that could be fed by that settled water. So actual settled water in the plant got diverted. Some of it got diverted over to a constant head tank and was fed into these three pilot filters, these three columns. One of those pilot columns was built to the existing specifications of the plant as the existing filters were. Then the other two pilot columns were built with some new media, new configuration of media that they wanted to test out and compare against the existing media. They put flow meters on them to be able to control the flow rate. They put turbidimeters on there to be able to control that or monitor the turbidity coming out. And they decided to run these columns at 5.7 gallons per minute per square foot to see which one produced the best water at the lowest loss of head. And it turned out that they got approval for one of those columns. So let's talk about that. To meet the requirements at that time, Ohio EPA wanted to see the filter design that could best produce at least 5,000 unit filter run volumes, and of course could meet regulations and could produce acceptable head loss. In addition to that, the design engineer wanted to have an L/D ratio greater than 1,000 and an intermix ratio of about 3. They wanted a low uniformity coefficient and the capability to operate at 5.7 gallon per minute per square foot. So eventually, when they ran these, they eventually designed the filter, chose the design of 24 inches of 1 millimeter anthracite with uniformity coefficient of 1.3 over 12 inches of sand at 0.5 millimeter size, effective size, uniformity coefficient of 1.3. And they put the IMS caps in there, which helped them gain space. So this is how it worked out. The old system was made of 3 medias: anthracite over silica sand over ilmenite, and that ilmenite was so much heavier than the anthracite. Look at the difference in the densities of them. It was only 3 inches, but very fine media, about 0.25, 0.3 millimeter. But the energy it took to expand that heavier ilmenite eventually just started to wash away all the anthracite. It just was a poor design back then. Everybody thought it was going to work well, and it did filter very well, but it did not backwash well over time. So that had to be changed. So the old filters looked a bit like this: 24 inches of 1 millimeter anthracite with a very high uniformity coefficient of 1.5, and then 12 inches of sand and 3 inches of ilmenite. They had a 6-inch gravel layer on top of 12 inches of Leopold clay tile under drains. So the head space they had for backwashing was only 31 inches. And because of that, the need to energize and expand that heavy ilmenite and being able to wash only through a column of 31 inches, they were losing a lot of anthracite there. The loading rate for those was 3 gallons per minute per square foot. So here's what they did with the new filter design. They were able to put in 24 inches of 1.1 millimeter anthracite over 12 inches of sand and IMS caps, load them very, very aggressively, but they had more head space for washing when they got through with this. If you notice, the total space taken on by the median support system for the old system was 57 inches, but the new system was only 44 inches. So they gained an extra 13 inches on top of the 31 to backwash through. So now they are working very, very well, and they're not losing media through backwash process. Just a couple of pictures to share with you. You notice that they got these dual media, or dual arm sweeps. This is the surface washers that were put in before the media was put in, so you can see what it looks like. The second arm lower is actually right at that intermix ratio of anthracite to sand, so it cleans that area a little bit better. Now, the bad things about these, you can't tell if that thing is running down in the second layer until you actually expand the bed. It won't run. So that's something to think about too. You gotta expand the bed sufficiently enough, get like a quicksand thing going before that second arm will actually move. So let's look at the filter media characteristics. I think this is the last slide or so for the new installation. The sand has an L/D ratio there of 12 inches. I multiplied it by 25.4, which converts the inches to millimeters, and divided by the effective size, and I get a value of 610. I'm going to do that the same thing with the anthracite because I'm looking over this L/D ratio that's got to be greater than 1,000. So the 24 inches of anthracite divided by its effective size gives me a value of 554. Now these values are additive. When I add them together, you notice that I come up with 610 plus 554, a value of 1,164. So I'm greater than that 1,000. This filter should operate naturally. Should do a very good job as long as I operate within parameters. The intermix ratio, remember I told you that should be somewhere around 3 to 3.5. You get that by taking the D90 coal size and dividing it by the D10 sand size. So that's a 1.669 divided by the 0.514. I get an average, or I get a intermix size of 3.24, which is right into that sweet spot that you wanted, somewhere between 3 and 3.5. So that should work out fine, and indeed it is. So that's the end of that. I'm going to stop sharing this with you and tell you to look forward to more topics that we should have coming soon. Thank you for paying attention.